Good morning. My name is Isaiah. This is my partner, Andrew, and we represent Team on Semiconductor, SMPS. So what does SMPS stand for? SMPS stands for Switch Mode Power Supply, and it's a voltage regulator that can take one voltage and create either a higher or lower value. And in our case, it's just a small electronic chip that's about 4 millimeters by 4 millimeters. Our project was to design a software package that would aid as a design tool for customers to simulate power supplies. Now, historically, if a customer wanted to simulate a power supply, they would have to use either Excel spreadsheets or MathCAD files, and we have an example of such shown here. And as you can see, the old process is actually very user-unfriendly, and it can be somewhat confusing to those who aren't familiar with switch mode power supply design. So our project would be a graphical user interface that would be more user-friendly and more intuitive to use. And here, we have a screenshot of what we created throughout this project. So when the customer loads up our project, this is the graphical user interface that they will see and they can use as their design tool. It is a little bit complex, and there are different parts to it, so we'll go over it one part at a time. In the first section of that graphical user interface, we have a schematic of the 891930, which was the chip that was the basis for our project. As you can see, you have the chip that's represented by a block here, as well as different external components that are used with it. And anything that you see that's in green, the user can click on and edit the component values for that particular component. They could even click on the thermometer if they wanted to and simulate the power supply over different temperatures. So when they do click on that component, they'll bring up the component editor as shown here. And here I have two different screenshots because the component editor actually changes dynamically based on which component they clicked on. So for instance, in the top screenshot, if they clicked on a transistor, which is a little bit more complicated, there'd be about 10 different parameters that the customer can edit. On the other hand, if they clicked on an inductor, which is a little bit more simple, there would be less parameters. And for some of our components, we actually recommend a value based on other design parameters that they've already entered. So as you can see here, we're recommending a value of 600 nanohenries for that inductor. This will greatly help the customer in their design process because we can remove a lot of the guesswork by providing values up front. We also have another option for the customer if they would prefer not to use manual entry boxes. Towards the bottom of that graphical user interface, we have a slider, and the customer can click on which parameter they want to edit and just move the slider to adjust that parameter. And while they're doing so, there's various design parameters that are being monitored. So towards the corner, we're monitoring the design efficiency of the power supply, as well as the duty cycle based on the parameters that they've entered. And once they have all their values entered, they can save their work by the buttons shown below. So we have two different save slots, and also if they get lost, they can just click on the Load Defaults button, and that will load up the default values that we're including with this software. Another accomplishment from this project is we introduced error checking so that if the user enters in a value that's not valid and it's outside of the lower or upper bounds, they'll trigger an error. And when that happens, all of the labels that are on the schematic will disappear, as well as the Bode plots will just graph zeros. So that will indicate to the customer right away that the value that they entered was not valid. And in addition, there's an error message at the top that tells them the component that was out of range, as well as what the range is for that component. Now my partner Andrew will talk about additional accomplishments from this project.
So in order to first start the design process, we begin by creating a flowchart which defines the intended functionalities of the tool, as well as showing the simulation options that ON Semiconductor's clients have, as well as the process of the validation of inputs. For instance, we show the very top part of our flowchart, which shows how we used our part configuration file. Next, we use unified modeling language to create activity diagrams for our design development tool. First, we made a top-level activity diagram which illustrated the workflow of the user. Then we created activity diagrams specifically for each part of the graphical user interface, which identified each of the possible use cases. On the right side of this slide, you can see a part of an activity diagram where the user will first select a value, then that value will be validated based on whether or not it fits within the minimum and maximum parameters of that specific component, and then ultimately that value will be set. Additionally, we use unified modeling language to create class diagrams specifically for each feature of the graphical user interface. Within these class diagrams, we identified each of the functions, methods, and variables that we would eventually use to implement each of those parts. On the right side of this slide, you can see a part of the class diagram that we used for our slider. Additionally, we were able to implement a fully functional slider, which the users of ON Semiconductor's product can use as an additional input mechanism. With this slider, there are two ways that they can use it. The first is they can physically move it in the left or right directions to their desired value, or they can use the text box to enter in a value, and that value will be shown. For example, for this resistor highlighted in green, the 1 ohm is reflected directly above the slider. Next, we were also able to achieve the ability to add in graphing capabilities to the tool. With these graphs, we were able to show the gain and phase response of the system for various frequencies. With each of the Bode plots, we were able to interactively display the crossover frequency as well as the gain margin. Then, when the user selects a frequency, we're able to show the gain and phase at that frequency. When looking at the left side of this Bode plot, you can see the crossover frequency and the phase margin. And for the frequency that the user selected right here, this is the gain and phase at that specific frequency. This was one of our team's toughest tasks, since in our prior experience with MATLAB, we never previously used it to implement features like this into any sort of design development tool. Ultimately, we were able to successfully achieve the anticipated best outcome of our project by being able to set limits on customer inputs, recommend values to the customer based on their inputs, graph performance and stability, and finally calculate power dissipation of the chip and its components. Ultimately, we would like to thank everyone that has provided us with support and guidance during this process. Thank you.